Hello everyone, I welcome you back to Winkle's class once again. Um, I want to say thank you very much to each and every one of you who was able to successfully watch the first episode that was specifically about understanding the molecular orbital diagram, the kind of things that goes into it, and the kind of molecular orbitals that we will be dealing with in this particular course or this particular series of videos that I'm going to be creating. And I would like to say a very big thank you for all those of us who was able to like the video and then shared it with our friends as well. Yeah. So for those of us who are new on this channel, those of us who have uh, not gotten the opportunity to watch the first episode, I would put the link in the description where you can just write. You can just follow rightly back and then go and watch it, because watching the first episode will help you understand today's content very well, because it is very important. It is just like a build up. Yeah, so for you to be able to follow up through and understand the whole UV spectroscopic process very well, it is very important for you to follow the videos episode by episode. Yeah, so if this is your first time, I would want you to help the channel grow by subscribing to the channel and also liking and commenting on the videos. All right, so that we can have that zeal to create more useful content like this. Thank you very much. So let's jump right into today's content. Today's content is basically about the spectroscopic process, okay, and it marks the second episode of our series that we are doing. Yeah, so let's move right into today's content. Let me display what we have today. Yeah, so this is what we are going to be dealing with today: the spectroscopic process in UV spectroscopy. Understanding UV-Vis spectroscopy, episode 2. Yeah. So in the UV spectroscopic process, there are few steps that we need to acknowledge or we need to pay much attention to. Right. And then the first of all these steps is the irradiation of sample, UV radiation. For you to be able to study a particular sample, so let's use this scenario throughout the lecture. Okay, you are going to be using this same scenario throughout, so just pay attention to it very carefully. Imagine you went into the lab and then your supervisor gives you, or your supervisor hands over a particular solution to you, and then he didn't tell you what the solution contains. It doesn't. You don't even know whether it was a sugar solution, a salt solution, or a particular chemical compound. You don't know. And then he asks you to help him characterize that particular solution. Okay. And then he wants you to start by using UV-Vis spectroscopy. All right. The first thing you have to do is think about exposing the sample to what? The radiation. All right. How do you do that? Most labs have the ultramodern spectrophotometer, where you can just put your sample in a cuvette and then put it in a machine, or the spectrophotometer where it runs the spec for you, right? Yeah, but then we want to understand what actually goes into it, what happens within the spectrophotometer. That is what we are looking at. All right, so let's say you have poured your sample into the cuvette, like this rectangular container is showing. You can see that this colored part of the container is what represents our sample, and I said sugar solution, so just for representation sake. Yeah, so this is our sugar solution, and then when you dip it into the spectrophotometer, we expect the sample to get irradiated by what? A UV source. Okay, now this UV, this can I don't know, this round structure represents our UV source. Okay, and then you will see that this dash 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 represents our radiations. All right, so the UV source has emitted its UV radiations on the sample. All right, this is what we mean by irradiation. Irradiation simply means exposing your sample to the source of radiation. So if I'm using, or I'm dealing with UV radiations, exposing my sample to the UV radiation is the irradiation process. If I'm using IR, that is infrared radiations, it means that exposing my sample to the infrared radiation is my irradiation process, right? It's just like shining a torchlight on an object, something like that. Yeah. So as you can see from the diagram, I think it's clear for you to understand what I'm trying to convey to you. Yeah. So for the first thing that you need to do, or the first thing that happens within the spectrophotometer when you put your sample into it, is the irradiation of the sample. All right. The UV source emits the radiation that goes through the sample. Right. So now, when the sample comes into contact with the radiation, what happens? That is what we are going to look at right now. Let's move on to the next slide. The second step, that is the electronic transition and absorption. So now your sample is in contact with the radiation, your UV radiation, right? We want to see what actually happens in there. How do they interact with each other? That is what we are going to look at. All right. But before that, let's take note of this. We know that every matter, okay, in science, matter is made up of what? Microscopic components, all right, that we can call atoms. Example. Yeah. So when you move right into the microscopic level of your sample, let's say the sugar, the sugar solution uh, in our scenario here. When you go to the microscopic level of this sugar solution, you would realize that we have atoms in there, and these atoms have electrons that are revolving around it constantly. Okay. Now, during this spectroscopic process, the electrons absorb some amount of energy, okay, that propels them to jump, or that propels them to a higher energy level or a higher orbital. Let me put it that way. Yeah. So the diagram on our left hand side, as the cursor indicates, shows that this particular sample that we are dealing with has what? Atoms within it. All right. So when you go to the microscopic level, you have atoms in there where we have electrons revolving around it. Is that not it? Exactly. Now, let's take the first point. It says that if a particular electronic transition matches the energy of a certain band of UV, it will be absorbed. Okay. Yeah. So when we talk about a band of UV, or when we talk about UV radiation, you know, from the previous episode, I showed you the uh, the how will I even say this? You know, from the previous episode, I show you the electromagnetic spectrum, right, which represents the individual radiations that comes together. You know, from the previous episode, I showed you the electromagnetic spectrum, right? And then you realize that each of the radiations have a range of wavelength that they operate with. Is that not it? It means that when you expose your sample to a UV radiation, it means you are exposing your sample to a range of radiation that possess a wavelength ranging from 100 to 350 nanometers, right? Right. So that you can simply break it down in this form. It's like you have radiation that has wavelength from 100 to 350, right? So it's like a group of radiations, right? Yeah, a group of radiations that makes, or that builds up that UV band that we are talking about. All right. Now, when you expose your sample to that group of radiations, there is a particular radiation among this group that has the energy that the electrons need in order to jump to a higher energy level. That is a basic explanation you can get from here. Okay. So let's move to the right hand side of the diagram. This rectangular structure represents our UV radiation. All right. You could see that there are different colors, right, from green all the way to black. There are different colors in here. These colors represents the different groups of radiations, or the different groups of wavelengths that we have within the UV band. Okay. Now, among this group of radiations, that is from 100 to 350 nanometers, each of them have some amount of energy, okay, that is associated with them. All right. And then this amount of energy is specific to each of the wavelengths. So it means that the radiation that has wavelength of 100 nanometers has an energy that is different from a radiation that will have 350 nanometers, right? Good. So looking at this molecular orbital diagram, you realize that we have two electrons on this bonding molecular orbital. This is the pi bonding molecular orbital, right? There are two electrons in here. Is that not it? Now, in order for this electron to be able to jump from this level to this level, that is from the bonding molecular orbital to the anti-bonding molecular orbital, it needs some amount of energy in order to successfully make the jump, right? Now, this energy is given to the electron by the radiation that we have exposed to the sample. All right. Now, let's say that where this black arrow is, this is the specific radiation that will be able to give this electron the energy that it needs in order to make the jump. All right. So what will happen? All the radiations will come into the sample because you expose your sample to it, right? Yeah. So all these radiations will be passing through the sample, right? But then this particular one that possesses the energy that is enough for this particular electron to jump to the next level will be absorbed by the electron. Okay, so when the electron absorbs this particular band of the UV radiation or this particular section of the whole UV radiation, it will be able to gain that energy that it needs to make the jump, right? So you realize that the jump has occurred and the electron has moved, one of the electrons has moved from what the pi bonding orbital to the pi anti-bonding orbital level. And you, as I said in the previous episode, you realize that this particular level has a higher energy as compared to this level, right? Yeah, so the energy, so for example, if let's say the energy absorbed by this electron is maybe let's say 130 kilojoules per mole, then it means that this particular UV radiation possess that amount of energy, right? That was why when the electron absorbed that radiation, it got that amount of energy in order to be able to jump from here to here. Do you get it now? So simply put, for an electron to be able to successfully make a jump from one orbital to a higher orbital, it needs some amount of energy. And that amount of energy is given to that electron by the radiation that you have exposed the sample to. All right? And what happens? The electron has to absorb that radiation in order to get access to that amount of energy. And that is what happened here. This particular section of the UV band was absorbed by the electron, and then the electron got the energy and then was able to jump from this lower energy level to this higher energy level. Please, are we okay? That is good. I'm sure you've understood what I've explained and you are now getting closer to the whole picture. Let's look at the second point. The remaining UV light passes through the sample and it is observed. All right. How do you know that a particular section of the UV radiation has been absorbed? It is through what you have observed. All right. This particular part, you will see that on our extreme right hand side, you will see that the rectangular structure here, this band, is not exactly as this. You will see that a particular part of it is colored white, whilst this particular part is colored black. Good. As I said earlier on, as the cursor, follow the cursor very well, you see that where the cursor is pointing to was the particular section of the whole UV radiation that the electron absorbed, right? Now you can see that that same section, when I match it, you see that that same section is colored white over here. It means that this section was absorbed, right? So the resulting spectrum, this particular rectangular structure is what we call a spectrum, right? The resulting spectrum is not the same as the initial spectrum. Okay, the resulting spectrum is what we call the absorption spectrum. It is an absorption spectrum because a particular section of it has been absorbed. It means that it is no more 100% as it initially was. Do you get it? Good. So, let's move on to the next slide. Formation of absorption spectrum. As I explained in the previous slide, the formation of the absorption spectrum occurs when the electron has successfully absorbed a particular band of the whole UV spectrum. Is that not it? Yes. So let me read what is written here. It says that the result is what we call an absorption spectrum, as I said earlier on. The result of the spectroscopic process is what we call the absorption spectrum. That is after the electrons have absorbed a particular section of it. It is like a fingerprint of the sample. Yeah, every sample has a specific absorption spectrum that it will give. Why? Because the kind of energy that the electrons will need in order to jump or to make the jump will differ from sample to sample, right? So if a particular sample gives you a particular absorption spectrum, then it means that you can use that particular spectrum to characterize the sample. All right. So in a situation where I said earlier on that your supervisor gave you a plain solution that you don't know what is within it or what it entails or what it contains, this particular spectrum, like when you run the spec and you get a spectrum like this will be able to give you an insight of what that particular sample contains or what the sample is made up of. Okay, so this is just a beginning of it. When you get this spectra or this spectrum, in addition to other useful informations or data, you'll be able to characterize completely the solution that your supervisor gave you. Okay, now let's continue the reading. It says that the gaps in the spectrum represents the energy absorbed by the sample. Exactly. Each individual gap that you see here, these dark spots, these black lines that you see here, each of them represents the band or the section of the UV that the sample absorbed, right? So when you gather all this information, when you take the wavelength, the specific wavelength that this particular thing occurred, the wavelength that this one occurred, the wavelength that each of them occurred, and you bring them together, you'll be able to get a useful data out of it, a data that you can interpret in order to elucidate whatever structure or the structure of whatever sample you are dealing with. All right, good. So let me put all that I said into a simple scenario or a summary. Let me put it that way. Yeah, so a summary of all that I said is just in 3 steps. The first thing is expose your sample to the radiation. That is, shine your UV light on the sample. Exactly. Now the second one has to do with what? Electronic transition and absorption. What happens when your radiation gets absorbed by the sample? The electrons within the sample absorb some part of the radiation that they need, or that they think will give them that amount of energy that they need in order to get excited towards a higher energy level. And once they are able to absorb that energy, they jump, as seen here. They make the jump from a lower orbital to a higher orbital. Okay. So after they have made that jump, what happens? You will get a resulting spectrum, and that resulting spectrum is what we call the absorption spectrum. Okay, that absorption spectrum will give you a useful information. What is that useful information? It will tell you the exact energy and then the exact wavelength of radiation that was absorbed throughout the process. Okay, and this is just a pictorial representation of how an absorption spectrum looks like. This is how it looks like. So the dark lines indicates the specific energies or the wavelengths that were absorbed during the process, and this together with other data will be able to help you get the exact content of whatever sample are dealing with. You'll be able to characterize the sample. You'll be able to predict the structure of the molecule that you are dealing with. Okay, yeah, so this brings us to the end of today's episode. Thank you very much for watching this video. I'm so grateful for you being able to stay all along from the beginning of this video to the end. I'm so grateful. Thank you so much for watching the video. I want you to help me grow this channel by subscribing to the channel. That is if you are a first timer here. And then also don't forget to like the video, don't forget to share it with your friends, and then don't forget to also comment if you have any questions or any suggestions that you want to bring. Thank you very much. I'll see you in the next episode. Bye bye.